Welcome back. You're now ready to explore the epidemic calculator that was used in the paper that you read in the last assignment. So you saw a lot of graphs that were produced in that paper. They came from the epidemic calculator that we have a link to right on our in the assignment. And so we want to understand how that epidemic calculator works. And then after this video, we'll update our MATLAB to do some of the things, not everything that's in that epidemic calculator. But it wouldn't be that hard to do everything that's in the epidemic calculator. We're just going to streamline it a little bit and code some of the features. So we'll have a pretty robust model of what's happening and very similar to the model that the experts are using. So let's switch over to the epidemic calculator. So here it is, the calculator being used by scientists and the author of the paper that you read. So let's see how we can use this calculator. First of all, there are boxes over here on the left. All right, if you check a box, it will tell you, it will show you over on the graph what is happening with that box. And you can see as I move this slider back and forth, the values of each category are changing and the numbers are actually being reported on the side. Now, unlike our program, I decided to make our time period weeks because we, the epidemic is sort of rolling out over weeks. This is being done by days. So everything in here is by day, so we'll have to alter it slightly as we put our numbers in, all right? So you'll notice there are categories. The S category is not being shown because it's going to be a very sizable population. So it's not very helpful to have a graph of S being shown because it would swamp the other data. So the exposed is being shown in orange, okay, or sort of a tan color. In magenta, the number of infectious people are being shown. All right, and then we have the removed population. All right, now they're only showing us part of the removed population, and they're assuming a couple of things about the removed that you might not consider. Somebody who is infectious but is in the hospital is being removed from the larger population. So in theory, they shouldn't be running into susceptible people anymore. So in this model, the hospitalized people have been removed. So that's the light blue category. Now that's in a very important category because that you saw in the paper, the hospital facilities only have so many beds. So if we have too many people who need to be hospitalized in the model, that is going to override our medical system. And then we have our fatalities being shown in dark blue. So you are removed if you are a fatality. So that would sort of fit what we had been thinking all along. So they've removed people, and they've also removed people who are recovered, but they're not showing it in the graph right now. Let me click that up and show you why. Because over time, the number of people who have recovered is very large. So once again, that swamps the data. And those who need to make plans about our medical facilities aren't too worried about how many people have recovered. Now, economists might be very interested in that. You read that second article. This green swath of people could go back to work. So the economists who wrote the second article had a valid point that all of these people in green could be back in the workforce as long as the tests come back showing that you can't get reinfected. So the verdict is still out on that. It seems like that would be the case. It's very bad news if the removed people can recycle back into the susceptible population. But this model originally didn't show that just because the other numbers look really small when compared to that over the long run. So we'll take that back out of there. These are the things that the medical workers are very, very concerned with that are left. So if we click on removed, it will show all of the removed. If I click off, it removes all of them, but then I can bring the hospitalized people and the fatalities back up, all right? And you can see how if I take all the removed in, take them all away. As I add things, you'll see how it pushes the other bars up in the bar graph. So this is being presented as a consecutive bar graphs here. It pushes the other bars up. It doesn't change the number, the numbers in orange or magenta. It just pushes them up. So these numbers at the top aren't totals because you have to take the top minus the bottom to get the total in any one category. If you want to see the total at any given day, you can look over on the left, and the numbers will follow, will be all are shown over there matching the bar of the bar graph that you're on. So you can see those over on the left. All right. Now, let me put our fatalities back in. An important thing is when the intervention happens, okay? And these, the most important parts of this model are up here at the top. So if we change when the intervention happens here, we're making the intervention earlier. You can see that's probably good. If we kind of wait around and don't intervene for longer, oh my goodness, we're off of our page. So we would have to rescale this if we wait later for an intervention. So I think the original intervention happened at 100 days. So I'll slide it back there, and it gave us a graph that looked like this. Now, before the intervention, you can see things are not good. Things are ramping up very rapidly. That's what would trigger severe interventions, and it looks like it's getting out of control. So things were ramping up, okay? And there are these things called the R values that we're going to talk about a little bit more in this video. This is an R naught, that's before the intervention of 2.2. What that means is that every person in purple, in the, or I should say magenta, in the infected category, while they're infected, should be infecting 2.2 more people. All right, so that's going to create sort of an exponential growth, and that's what you see here, an explosion in the number of exposed and infected people, which will in turn drive people to the hospital and will also cause more fatalities. So if we don't intervene, you can, there's just this runaway train effect. You can see the fatalities begin to grow very, very rapidly. Probably the only reason they're dropping off by now is that we have probably run out of people to infect. So the fatalities will level off as you have no more people to infect. So we don't want to do that, and we're not clearly not doing that. We're in the middle of interventions, which is why I'm giving you this class on video right now. And so we switched over to this second R value. So this is RT. This is to decrease the transmission. So they're calling it RT now. And we'll probably call them R1 and R2 to match our data in MATLAB. But you can see this is kind of a quirky thing. If I move the slider to the left, it looks like it's getting worse. You would think that moving the slider to the left would make RT go down, but look at the number. It's actually going up, and so things get worse, all right? It's better than when they were 2.2, when R was 2.2, but it still takes a while to come down. You can see that if we can get this down below 1, good things begin to happen, okay? So once we drop this below 1, we're going to see that the curve starts to bend the other way. Okay, so we can make the curve, you hear in a lot of reports right now, bending the curve, okay, or flattening the curve. So when we can make R less than 1, it means that each person who's infected will infect less than 1 more person. This graph starts to do better things, all right? And what the medical people are really worried about is that light blue area. Okay, so if we can make our R go down, you can see that the light blue peak is dropping sort of slowly here. If we bring the transmission rate all the way to 0, we still have a significant peak there. A lot of people still will be hospitalized, but you can see as we raise that transmission rate, that hospitalization number shoots way up. Okay, the fatalities are growing as well, but the hospitalization rate goes way up. What our medical experts are most concerned about is that when this, as you saw in the paper, when this hospitalization rate goes up, the fatality rate probably would increase because if people who need to be in the hospital can't get into the hospital, they're very likely to die. So our fatality rate would change, which is something that this model isn't doing right now, that we will try to take into account in our MATLAB model. So as soon as there aren't hospital beds, the fatality rate will go up significantly. Instead of being 2% or 1%, it's much more likely to be 5 or 10%. And as the paper talked about, there will be fatalities to other people who don't have coronavirus who simply can't get a hospital bed. So if somebody were to have a heart attack, medical resources are strained, there won't be an ambulance to pick them up, and they probably would become an incidental fatality that might not be counted in this number. So real fatalities may be even worse. So a real goal is to keep this hospitalization number down to a manageable level, so that our facility capabilities will match the needs. Now, another thing you'll see, okay, down here below the video, we can change all kinds of things like, so these are lesser things to be able to change. So we can change the R naught value. I think that's going to change as we raise that up. Oh, what's happening here is this was before we did interventions. So you might end up killing everybody prior to ever doing an intervention. So that's not a good thing. If this R naught value is going up, we don't want that to happen. So another part of the model that's important is the transmission time. Okay, so if we change how long the incubation period is, that's how long people who get exposed will take to become infected. Okay, so it actually delays the curve if the incubation period gets longer. The number of exposed people, it takes longer for the exposed population to switch into the infected population, so it drives everything over to the right. Doesn't necessarily make it better, it just delays the inevitable. Okay, so this incubation time creates a delay between people getting exposed and actually manifesting symptoms. We can also play with TINF, that's the time for which people are infected. If we lower this time, we can see that the magenta region definitely gets smaller. All right, they're less likely to infect other people if that goes down. In conjunction with the R value going down. You would assume that if they're infected for less time, they will infect fewer people, but you would have to actually change the R value to go down proportionately as well. So if you were to change that number. Let's see, what else can we do? If we change the length of hospital stays, for instance, we can see, less hospital time. That is good news for our medical people, because we'll have far fewer patients waiting in the beds if they don't need to be in the beds as long. If they need longer to be in the beds, that number changes. So that's those are the things that we can play with. Okay. Now here are the differential equations. So we had, let's see, it looks like we're still recording. Let me pause for a moment and go. Sorry about that. I meant to pause the video and I meant to get a marker so I could annotate the video and I accidentally stopped the screen share. So here we are. These are the differential equations. They look a little bit like what we had before. Okay, we have a ds dt and there's an I times s, but there's no a. We were expecting to see an a here. Sorry, this writing with my little touchpad is hard. We were expecting over here to have this be our A value as we looked here, and we were expecting a B value here. All right, and so on and so forth. We were expecting this to be a B and then a C, and then we were expecting the last one to be a C as well. All right. So we're going to need to talk about why these are different from that. And this is the more scientific way of expressing A, B, and C. So let me switch over to my iPad and try to explain what those T values are. Turns out they're called time constants, and we want to explore what those mean.